Okay, let's start. Hello, everyone. Welcome to the next episode of the Warsaw Quantum Computing Group meetup. It's already episode 69, but the first episode in the academic year 2025-2026. My name is Paweł. I'm also the main organizer of this meetup, or actually, I organize it on behalf of the Quantum AI Foundation. I will later tell about the Quantum AI Foundation, a few words about our activities, as this could be interesting for some of you if you want to learn more about quantum technologies and or artificial intelligence, because we organize different events, activities related to uh, mainly these two topics, AI and quantum technologies, but we also support other new technologies as well. Today, I will give an introduction to quantum computing, and I will also say a few words about the ecosystem of quantum technologies in Poland. Uh, let's start, but before we start, I would like to thank our strategic partners for supporting us. These are interesting companies, mainly from Poland: R&D, Sonovero, Quantum.io, Onyx, QLab, Cogit, and ThinQubit. I would also like to thank our honorary partners. There are more of them, so I will not tell the full names, but you can see the list. You can check the list on the website of the Quantum AI Foundation and the Warsaw Quantum Computing Group meetup. So this is the plan for today. So first, I will tell you a few words about the Quantum AI Foundation and the Warsaw Quantum Computing Group meetup. Then I will give an introduction to quantum computing, and then I will tell about some potential applications of quantum computers. Then I will uh, share my perception of the state of the quantum computing domain, what's the progress, what are the obstacles, and so on. And finally, I will tell about the quantum computing ecosystem that is emerging now here in Poland, but also worldwide, of course. And I'm lucky to be engaged in these activities, both at the global level and here at the national level. And finally, there will be time for Q&A, but if there are some urgent questions, you can also post them on the chat, and mm, after every section, I will try to check the chat to see if there are some questions that should be answered. I can also ask you to unmute and ask your question or clarify something. All right, and maybe one last thing. As you can see, this meeting is recorded, so hopefully the video will be later available on our YouTube channel. Okay, so we can start. A few words about the Quantum AI Foundation, or actually formally it's called Fundacja Quantum AI in Polish. It's a non-profit organization that I established in 2019 in November, and so I'm the founder and I'm the CEO. And basically, our goal is to support the development, research, and collaboration in science and new technologies, especially AI and quantum computing, but also other fields of math and computer science. Mm, we do it by organizing different educational activities like Warsaw Quantum Computing Group meetups, this meetup, workshops. We formally support Q Poland, which is one of the Q cousins of QWord. So in the last section of this talk, I will also tell about QWord more. We also organize hackathons, contests. We release a monthly newsletter, Q Poland newsletter, and similarly, we have several activities in the domain of artificial intelligence. So this meetup is a meetup for quantum computing enthusiasts in Warsaw. But so actually, before the pandemic crisis, all the meetings were on site. Later in 2020, we started organizing online only meetups. And now, from time to time, we try to meet in person in Warsaw, usually one or two times per year. So this year we had on-site meetings in April when there was a World Quantum Day, and later in May there was a talk given by a person from IQM. But usually our meetings are online so that participants from all over the world can easily attend. So our goal is to facilitate education and research collaboration of people interested in quantum computing, building quantum computing awareness, and building the community of quantum computing specialists. So each meeting, like this one, consists of a lecture. Some of the lectures are followed by an after party if we organize them on site, when our participants can interact and exchange ideas. So as I said, initially the meetings were on site. They were organized in several locations in Warsaw. The spaces from Facebook, Google, University of Warsaw, Code Cool. But later our meetings were mainly online. But as I said, we plan to have 2 free on-site meetings per year. We record our lectures and make them available on our YouTube channel, so you can easily find the channel of the Warsaw Quantum Computing Group on the YouTube. We started organizing these events in 2018, in November, close to November 11th, to commemorate 100th anniversary of regaining independence by Poland. And as I said, the meetings are more or less once per month. Beside the holidays, we usually do a summer break. And here you can see some useful websites and links to our YouTube channel, to our website, to our profiles on social media. We also have a mailing list so that if you join, you will be notified about our other activities as well. Okay, yeah, so do we have any questions on the chat? Um, I do not see any questions, but I can see that we already have 44 participants, which is good. The interesting thing is that we had almost 200 signups, which is one of the best results in this meetup. This is really great. So thank you for such a great interest. So now I will just go directly to the introduction to quantum computing. So a very important and fundamental question, what the quantum computing actually is. So of course there can be a simple but too simple answer that these are computations according to the laws of quantum mechanics. But in the next slides, in this section of my talk, I will try to explain more technically and in detail what these quantum computations are. But even in the simple answer, we have the term quantum mechanics, right? So in both terms, quantum computing and quantum mechanics, we see the word quantum. So what does the word quantum actually mean? So in science we do not cite Wikipedia, but for the purpose of this popular science talk, I decided to provide a citation from Wikipedia, as I think this is quite useful and available for the broader audience. So in physics, a quantum is a minimum amount of any physical entity involved in an interaction. And this means that the magnitude of the physical property can take on only discrete values consisting of integer multiples of one quantum. And we know it. We know that our physical world is inherently quantum from the beginning of the 20th century, more or less, when the Max Planck's postulate was formulated. And this postulate basically says that the electromagnetic energy could be emitted only in the quantized form. So we have the formula for the energy of the photon or electromagnetic wave. We have the Planck's constant, and we have a frequency of a photon or electromagnetic wave, and we have integer numbers. So we can see that these amounts of energy can be only um, proportional to the Planck's constant multiplied uh, by the frequency, and there is also an integer multiplier here involved. Um, okay, so and this, of course, this has very important consequences, right? So because at the beginning of the 19th century, some researchers thought or believed that uh, the physics is almost complete, that we know about our physical world almost everything, and there were just, let's say, several open questions for which the researchers expected to find good answers, solutions in the nearest future, but the reality was different. So it turned out that this Planck's postulate um, caused the beginning of the new area in science, in physics, and later it led to the development of the quantum mechanics theory and formalization of quantum mechanics as well. So nowadays we know that we live in the physical world that is quantum at the bottom, and it has some important consequences because when we talk about computing, we can talk about the algorithms, we can analyze the computational complexity of our algorithms and try to prove their correctness. But at the end of the day, we would like to run our algorithms or implement our algorithms as computer programs and run them on physical devices, physical computers. And these physical devices are governed by the rules of our physical world, which is quantum, and it may have some important consequences. So just one of the consequences of the fact that our computations are run in a physical world is the Landauer principle, which says that there is a minimum possible amount of energy required to any logically irreversible manipulation of information, like erasing one bit of information. And here we can also see this minimum, the formula for this minimum amount of energy. And in this case, we have the Boltzmann's constant involved, and there is the temperature of the environment in kelvins. Okay, so we know that we have to take into account the physical laws when we want to discuss some limitations of computing and running computations. And actually, many years ago, researchers already started thinking about the limitations of computing. So very famous physicist Richard Feynman said that there's nothing that I can see in the physical laws that says the computing elements, the computer elements cannot be made enormously smaller than they are now. So it was 1960. And he said, in fact, there may be certain advantages. And indeed, if you know the history of computer science, then you know that um, the first computers were very, very large. So the computers in 40s or 50s of the 20th century were very large. So the structure was different than the structure of the computers that we know nowadays. But already at the beginning of 1960s, researchers uh, realized that the we are able to make the computing element smaller. And there was an observation formulated by Gordon Moore, which is now known as the Moore's law, which says that the number of transistors in a dense integrated circuit doubles about every 2 years. So initially it was even faster, once per 1.5 year, more or less. And now it is already even smaller. It's once per 2.5 years or once per 3 years, maybe already. But this prediction proved accurate for several decades and has been used in the semiconductor industry to guide long-term planning and to set targets for research and development. Um, yeah, but already about 10 years ago, Gordon Moore says that he sees Moore's law dying here in the next decade or so. And Intel, the company developing microprocessors, has also realized that the pace of advancements has slowed. Uh, so at that time, it was once per 2.5 year. This doubling of the density was once per about 2.5 year. So this trend will continue. Perhaps still uh, it can still be getting slower and slower, of course. But the question is if this trend can continue forever. So if this trend has to be continued for the next years, then about 2035 or 2040, the size of a single transistor should be of the size of a single atom. And in such a small scale, the transistors that we know cannot just operate as as they operate nowadays in at larger scales. So it's natural to ask how we could perform computations on such a scale, uh, if we want to do it, of course, if we want to speed up our computations. And the same Richard Feynman in 1980s already said that we can in principle make a computing device in which the numbers are represented by a row of atoms, with each atom in either of the two states. That's our input. The Hamiltonian starts Hamiltonianizing the wave function, the ones move around, the zeros move around, and finally a long particular bunch of atoms, ones and zeros occur that represent the answer. Nothing could be made smaller, nothing could be more elegant, no losses, no uncertainties, no averaging. But can we do it? So that was the question. And as we have the Warsaw Quantum Computing Group meetup, and I'm giving a talk to talk about quantum computing and introduction to quantum computing, you probably know that the answer is positive in some sense. So we already have some quantum computing or quantum processing units. So some people still do not call them as, let's say, real quantum computers because, as you will learn later in this talk, these contemporary quantum processing devices or machines are still imperfect. But we already have some achievements. We already have some, let's say, quantum hardware that can perform some computations. And there have already been articles demonstrating some kind of quantum supremacy or quantum advantage over classical computers. So here you can see on the left, you can see the Bristlecon, which is one of Google's quantum processors. And on the right, you can see a cartoon of this device where each X represents a qubit with nearest neighbor connectivity. All right, so we know that we can build some quantum processing units, but it's important to understand what's the difference between classical computers and quantum computers. So in case of classical computers, we have bits and classical gates. You probably know the classical gates like AND, OR, NOT, and you know that the bits may have one of the two possible values, 0 or 1, and they can be given as an input to our classical gates. They can produce an output based on the logic of the given classical gate, and the output from one classical gate can be an input to another classical gate. So this is the idea of classical computing, more or less. Of course, it's simplified, but these are the basics, right? So these are the building blocks of classical computers. But in case of quantum computers, we have qubits and quantum gates. So we have these quantum bits. So what's the difference? So I've told you that in case of a bit, we know that the state of a bit may have one of the two values, 0, 1. So it can be just an element from the set 0, 1. So mathematically, it's something uh, very simple. But the qubit state can be a superposition of states 0 and 1. And what is this superposition? So actually, when we have a superposition, it means that our qubit carries some information about the states 0 and 1 at the same time. And mathematically, it can be represented as a unitary vector of the two-dimensional Hilbert space over complex numbers. So you can see the difference, and you can see that even mathematically, it's more complicated. I believe that most of you or all of you know what are the unitary vectors. Many of you have heard about complex numbers. Some of you have heard about Hilbert spaces as well. But in general, it seems to be more complex. So what are the other differences? So in case of classical computers, the state is determined. So we can know exactly whether the state is 0 or 1, and it can be changed from 0 to 1 and vice versa. In case of quantum computers, to get values 0 or 1, we have to do a measurement that breaks the superposition. And we have some probabilities of getting 0 or 1 after the measurement. And these probabilities depend on the state of a qubit. So on this unitary vector of the two-dimensional Hilbert space over complex numbers. And quantum gates can modify the qubits and they can modify this probability or distribution of probability. So this is a, let's say, visualization or formula visualizing the superposition of states 0 and 1. So here we have the state 0, 1. So you can see that we have this specific notation that is called the cat notation or Dirac notation. So sometimes we call it 0 cat or 1 cat. And A and B are complex numbers. So we have superposition of this state 0, 1. And how we should think about the state 0, 1. So in case of classical computers, we think about them as not just numbers, 0 or 1. But in case of quantum computing, we should think about them as some vectors. But they cannot be, let's say, arbitrary vectors. They have to form an orthonormal base of our quantum system. So, for example, we can think about them as vectors 1, 0 and 0, 1 in two-dimensional space in this case. And A and B are complex numbers, but they also cannot be an arbitrary complex numbers because we know that the squares of their amplitudes uh, determine the probabilities of getting 0 or 1 in a measurement so that the sum of the squares should be equal to 1. Um, and from the, um, let's say, arithmetics of complex numbers and some physical properties of quantum systems, um, so we can find a complex number such that when we multiply a by this complex number, we'll get a real value. And by this multiplication, uh, will not actually change the physical properties of the quantum state because what is important is the difference in a phase between the two complex numbers and not the exact phase. So multiplying these numbers a and b by a unitary vector doesn't change the quantum state. And the consequence is that a and b can be transformed to spherical coordinates. So if you are interested, so here is at the bottom, you can see the mathematical formula for this transformation. And what is important, what is the consequence is that we can also think about the states of qubits as points on a sphere that is called the Bloch sphere. And so here, for example, right, when we have a given point on the sphere, it is determined by two angles. And these two angles also determine a state of a qubit, a superposition, right? These coefficients in front of the 0 cat and 1 cat. So in this case, the states 0 and 1 are antipodic points on this sphere. And so in classical computers, the bit state can be just one of these points. But in quantum computers, the qubit state can be any point on the Bloch sphere. And what is also important is that when we perform computations, as you will see, uh, at least for a single qubit for now, these computations correspond to rotations of this sphere around some axis. Um, yes, so that's why sometimes we say that quantum computing for a single qubit, of course, is a journey on the Bloch sphere. So I've already have started talking about quantum gates, so let's check what are the examples of quantum gates. So here you can see some notable popular examples like the Hadamard's gate. So here you can see that this is in case of the Hadamard's gate, the state 0 is transformed to the superposition of state 0 and 1, such that the probability of getting 0 and 1 after the measurement is the same, 50%. And analogically, we can transform the state 1 using this Hadamard's gate. Pauli X gate, as you will see, it corresponds to the rotation around the axis X, and it corresponds to something like the quantum negation. So the state 0 is transformed to the state 1 and state 1 to state 0. Y Pauli gate, it corresponds to rotation around the y-axis, and Z Pauli gate corresponds to the rotation around the z-axis. And these rotations can be parameterized as well. So for example, we can parameterize the rotation around the y-axis, and this is the formula where this angle phi is a parameter in this case. So especially this parameterized gates are very important for contemporary quantum machine learning, like variation quantum algorithms. So it's good to know that these quantum gates can be parameterized. And of course, we can act on more qubits at the same time, so more than one qubit. So for example, a CNOT gate, uh, CNOT gate operates on 2 qubits, and 1 qubit is a controller for the NOT, so this X Pauli operation on the second qubit. So I will explain it later on the next slides. And it turns out that any quantum circuit can be simulated to an arbitrary degree of accuracy using a combination of the CNOT gates and single qubit rotations. So, of course, in practice, in quantum computations, we can use some other more advanced gates. There are also gates operating on more than 2 qubits, of course. But it's good to know that at the end we can represent our computations using CNOT gates and quantum gates operating on a single qubit. So corresponding to rotations around different axes on the Bloch sphere. So a few words about the Hadamard's gate. So we can see the formula once again. We can see how the state 0 is transformed to the superposition of state 0 and 1. The probability of getting 0 or 1 after the measurement is 50%. So it also represents a rotation of 180 degrees around the axis x plus z. And alternatively, it's a composition of 2 rotations. First, we can rotate by 90 degrees around the y-axis and then by 180 degrees around the z-axis. And what is also important, so I've told you that in case of a single qubit, we are in a two-dimensional Hilbert space. So in particular, it's a linear space. And these operations correspond to just linear operations. So in fact, there are even unitary operations. So for all these kind of operations, we have a matrix that determines how exactly our vectors are transformed, right? So I've told you that we can think about the state 0 as the vector 1, 0 in our two-dimensional space, about the state vector 1 as the vector 0, 1. And then when we have a matrix of our operation, we can just multiply this matrix by the initial vector to get another vector. In this case, when we multiply this matrix by y 0, 1 and 1 and 0 vector, we can get yeah, exactly this vector. So vector 1 over square 2 and 1 over square 2. So positions in this vector correspond to coefficients in front of the 0 ket and 1 ket. So for the X Pauli gate, it's even simpler in this case. So as I said, it's an equivalent of the NOT gate, quantum negation. And it represents a rotation of 180 degrees around the axis X. And here is the Pauli X matrix. Similarly, there are also matrices for other rotations. So this is a matrix for this parameterized rotation around the y-axis by the angle phi radians. Yes, and here we can also see visualizations of these quantum gates that we can uh, use when we draw quantum circuits. I will later show you an example of such a quantum circuit. And finally, CNOT gate, right? So I've told you that this is a gate acting on 2 qubits, and it performs the NOT operation on the second qubit when the first qubit is 1, and otherwise it leaves it unchanged. So when we um, apply this quantum gate, the qubits are entangled, and this is the CNOT matrix uh, for the CNOT gate operation. So in this case, you can see that it's a 4-dimensional matrix, and we are also in a 4-dimensional space. So here we have 4 basis vectors. We can also think about them in this way, right? And in general, when we operate on n qubits at the same time, uh, uh, and apply the quantum gate operating on n qubits, we are in 2 to the power of n dimensional space. So it grows exponentially. And actually, this true power of quantum computing comes uh, with many qubits, actually, right? So not one, but when we have many qubits. So for example, in this case, let's assume that we have n qubits at the beginning, then we apply the Hadamard's gate to every single qubit. Yes, so we are in a superposition at the end of all possible 2 to the power n-bit numbers in this case. And then we can apply uh, another combination of quantum gates. And yeah, then you can modify the probabilities of getting each of the each of the possible 2 to the power of n states at the end. So that's the idea, and here is an example just to demonstrate how to use it. So let's assume that we have 8 qubits at the beginning, 8 quantum registers, and they're initialized to the quantum state 0, 0 ket. And here at the bottom we have 8 classical registers where we can store the results of our computations after the measurement. So here we have the measurements at the end. And what do we have here, right? So let's look at the qubits number 3, 5, 7. Initially, their state was 0. There was no quantum gate applied acting on them. So when we perform the measurement, in theory, the result of the measurements should be 0. I tell in theory because in practice there can be noise in our computation. So with a non-zero probability, we can get another value. But in theory, the result should be 0. In case of the qubit number 6, we apply the X Pauli gate. So in this case, so this visualization was prepared in the IBM Q experience, and this representation of the X Pauli operation is a bit different. So it's like a plus in this case. So it's a quantum negation. So the initial state was 0. After applying this gate, we are in the state 1, 1 ket. So when we do the measurement, the result should be 1. And an interesting situation is in the case of qubit 0, 1, 2, and 4. So let's look at the qubit number 4. We apply the Hadamard's gate. So initially the state was 0. So after applying the Hadamard's gate, as you remember, hopefully, we are in a superposition of state 0 and 1, and the probability of getting 0 or 1 after the measurement is 50%. And then we also apply the X Pauli operation, but it still gives us a 50% chance to get 0 or 1 after the measurement for the qubit number 4. But the qubit number 4 is here entangled with qubit 0, 1, and 2. So we have the CNOT gate applied to them, and the qubit number 4 becomes a controller for qubits 0, 1, and 2. And what is the consequence? As you remember, um, the state of qubit 4 determines uh, the results, or the result of the measurement of the qubit number 4 determines the result of the measurement for the qubits 0, 1, and 2. So if the result of the measurement on the qubit number 4 is 0, and we know that it's in 50% of the cases, more or less, so the probability is 50%, then for the qubits number 0, 1, and 2, the result of the measurement will be 1. And vice versa, if the result of the measurement for the qubit number 4 is 1, then the results of the measurements for the qubit 0, 1, and 2 will be 0. So there are two possible results of the measurements, right? So reading from the qubit number 7, here we always have 0, here we always have 1, 0. Here we can get the value 0, then on qubit number 3 is 0. As here we had 0 on the qubit number 4, then for qubit 0, 1, and 2, it's 1, 1, 1. So this is the first result, it's the letter G assigned. And another possible result, second possible result, 0, 1, 0, 1. So it determines that the results of the measurements for 0, 1, and 2 should be 0, and for the qubit number 3, the result is 0 as well. So we have another possible results. Here we have the letter P, and it's not by accident because these are just the ASCII code representations of the uppercase letters P and G, so my initials in this case. So we can say that on these 8 qubits, after applying this quantum circuit, we stored two 8-bit numbers at the same time. We just modify the probability of uh, getting uh, different 8-bit numbers uh, at the end, right? So in this case, the probability is 50%. So you can do a similar exercise for your initials, of course. So this is one of the consequences of having qubits instead of bits. So in case of classical computers, on n bits we can process only one n-bit number at the same time. But in case of quantum computers, using n qubits we can process all 2 to the power n n-bit numbers at the same time. In case of classical computers, the results are deterministic and randomness is actually a pseudo-randomness. And we even apply the generators of the pseudo numbers. We can apply different seeds for these generators, and thanks to that, we can repeat our computations. But in case of quantum computers, we may get a real randomness um, and easily sample from probability distributions that are difficult for classical computers. So later I will give you an example. For example, there's the Boltzmann distribution that exists in classical machine learning, um, and this is quite difficult for classical computers, but it's more natural for quantum computers. Um, and actually, here I said that in case of quantum computers, we may get the or achieve the real randomness. So here is also a star, small star, because actually we what is the real randomness in our physical world, or actually what is the randomness? So it's a bit of so somehow scientific question, but also somehow philosophical question, because there are different interpretations of quantum mechanics, and in according to some interpretations, the whole world, the universe is, or the evolution of the universe is deterministic, but we can observe only one of the possible realizations. Um, but from the perspective of the observer, uh, we can observe something like randomness, right? So we can think about the randomness as the randomness that we can get from the quantum mechanics, from the observing quantum systems. Um, all right. So that was an introduction, the first merit part. And let me check if we have any questions on the chat, or maybe some of you would like to uh, unmute and ask a question. Then feel free to raise your hand. All right. So we have people with different background, especially different background in math. So it's really hard to adjust the material properly, but I hope that it was understandable for everyone. Okay. Um, I do not see any questions, so let's go to the next section about the potential applications of quantum computers. Um, yes, so I've already told you about some possible advantages, or at least theoretical advantages of quantum computers over classical computers. So the natural question is how exactly these advantages can be exploited by us to achieve some advantages in practical computations. Um, so, in general, it's good to know that contemporary quantum computers are still relatively small. They are noisy. They are imperfect. It's difficult to scale them, right? So it's hard to expect some serious applications in the near future, but there are already some scientific works and publications of companies um, demonstrating a usage of uh, quantum computers to solve some problems. It doesn't mean that we have the supremacy, the practical supremacy already, but at the later in this talk, I will tell you about one scientific paper from this year claiming that we already have the practical quantum supremacy. But it's good to know what are the theoretical applications and where we could expect some advantages in the future, at least in theory. So it turns out that we can use quantum computers to break some classical cryptography algorithms. Um, and I will tell you more about it soon on the next slides. It's related to solving the factorization problem in polynomial time. There is the famous Shor's algorithm to do it. But it's also good to know that there is a field of quantum cryptography or even broader quantum communication. So it's not exactly quantum computing, but it fits the broader scope of something that we can call the domain of quantum technologies. Right? So in this domain of quantum technologies, we have this quantum communication, quantum key in particular quantum key distribution. We have quantum sensing, quantum metrology. So it's good to know that there are also some other quantum technologies other than quantum computing. And actually, their real-world applications can be even earlier. So there is a potential for some earlier practical real-world applications of the other quantum technologies, so not necessarily quantum computing. But going back to quantum computing, they can be also applied to solve combinatorial optimization problems, and these problems frequently occur in machine learning, for example, AI. So the contemporary AI is almost entirely machine learning, and the whole machine learning is all about optimization. So when we train our neural networks, we just look for good set of values of weights of connections between our artificial neurons in order to optimize, to minimize the loss function. So this is just an example. In case of other more classical machine learning algorithms like decision trees or k-nearest neighbors, there are usually some objective functions that we just minimize, and we fit some parameters to minimize some values on our data set. So the optimization problems frequently occur in AI and machine learning, but they also frequently occur in finance, optimizing the portfolio, for example. They frequently occur in transport, logistics, in the energy sector as well. I will show you some examples on the next slides. We can also sample from difficult distributions. We may have quantum random number generators. There are already such devices that you can even buy that can for which you can verify that some sequences were generated using quantum way and not classical way. We can simulate some quantum processes, and this may have applications to discover new materials, new drugs. We can search in unstructured databases using Grover search algorithm. We can generate art, like generate music. There are some nice research articles on generating music using quantum computing. So these are just some examples. And if you want to ask where we can expect some advantages of practical applications in the nearest future, or where will be the first applications. So most of the researchers I talked to and asked about it think that this fourth point, simulating quantum processes, simulating chemical reactions to discover some new materials, new drugs. So in general, this quantum chemistry could be or is considered to be, let's say, the most promising area. All right, but let's start from the factorization. So in the factorization problem, we have a large number with many qubits, or sorry, many digits, many bits, and we have to factorize it. So when we have two n-digit numbers, we can easily multiply them, right? So we can easily do it. So In our schools, we learn how to do it in a square time. This is an interesting thing that just recently, a few years ago, an algorithm performing multiplication of two n-digit numbers in n log n was published. Um, but the problem of factorizing n-digit numbers is considered to be difficult, and this assumption was used to design some contemporary uh, cryptography algorithms like RSA, for example. What is interesting, no algorithm has been published that can factor all integers in polynomial time. But what is for me even more interesting is that neither the existence nor non-existence of such algorithms has been proved. So it's generally suspected that such algorithms do not exist and hence that the problem is not in class P. Because in general, in computer science, it's usually easier to find an algorithm uh, when the algorithm exists than to prove that an algorithm doesn't exist if the algorithm doesn't exist. For many years, researchers were thinking about fast algorithms for factorization. The best published algorithm in terms of the asymptotic time is the general number field sieve. So we can see what's the time complexity. So it's sub-exponential, but it's more than polynomial time. And of course, there are some algorithms for some special cases. So this is one of the reasons why when we apply these popular cryptography algorithms like RSA, we have to be careful with selecting the keys, just not to fall in the trap uh, that we can generate an instance that can be easily solved. So using classical computers as well. But we know that we can perform the factorization in polynomial time on quantum computers. There's the famous Shor's factorization algorithm. So here we can see the time complexity and the visualization of the circuit. So here we can see Hadamar's gate, but of course, the one of the most important parts. So actually, this is a hybrid algorithm, right? So there is a part of computing that is performed can be performed on classical computers, but there's also a quantum part, a quantum subroutine responsible for finding a period of a long sequence using the inverse quantum Fourier transform in this case. Okay, so that was another example, and another one is solving combinatorial optimization problems. So what are these combinatorial optimization problems? So in this kind of problems, we search for the best of many possible combinations. So these problems include scheduling challenges like, should I ship this package on this truck or the next one? Or what's the most efficient route a traveling salesperson should take to visit different cities? So physics can help solve these sorts of problems because we can frame them as energy minimization problems. And the fundamental rule of physics is that everything tends to seek a minimum energy state in closed environments, at least. So objects slide down hills, hot things cool down over time, and this behavior is also true in the world of quantum physics. And we can take advantage of something that is called quantum annealing, for example, that uses quantum physics to find low energy states of a problem and therefore the optimal or near optimal combination of elements. So now I will tell you more about this quantum annealing, and to do it, it's first good to introduce something that is called adiabatic quantum computing. So first, what is the adiabatic process in physics in general? So it's a process that does not involve the transfer of heat or matter into or out of a thermodynamic system. So the energy is transferred to the surroundings only as work. And there is an idea for an adiabatic quantum computing that can be described as follows. So first, a potentially complicated Hamiltonian is found, whose ground state describes the solution to the problem of interest. And next, a system where simple Hamiltonian is prepared and initialized to the ground state. So here I use the word Hamiltonian, and I haven't introduced it earlier. So for a purpose of this lecture, you can think about a Hamiltonian as a function that takes a given quantum state of a quantum system and returns the energy of the system in the state. Um, so finally, the simple Hamiltonian is adiabatically evolved to the desired complicated Hamiltonian, and by the adiabatic theorem, the system remains in the ground state. So at the end, the state of the system describes the solution to the problem. What is very interesting from my perspective is that this adiabatic quantum computing has been shown to be polynomially equivalent to conventional quantum computing in the circuit model that I introduced at the beginning, right, with all these quantum gates. There's a paper about it. So at least in theory, we can, let's say, transform one computational model to another, but we do not do it in practice, right? So this, let's say, polynomial introduces additional overhead, and anyway, our contemporary quantum computers are still too small to do such things, I guess. And so it will not be, efficient enough for us at the beginning. So this is a visualization of this procedure that I described, right? So we have this initial Hamiltonian for which the ground state is easy to prepare. So this could be, for example, just a superposition of all possible states after the application of the Hadamard gates. And then we have the final Hamiltonian corresponding to the so-called LXIX model. So I will soon explain this LXIX model in details. And in this final Hamiltonian, with the letter F, the ground state should correspond to the solution of our optimization problem. And then by changing the values of S slow enough, the final state should be the solution of our problem. And in practice, this, let's say the value S, can be changed by modifying the strength of the magnetic field. So here we have several problems. So first of all, um, it's really cannot, it's difficult to guarantee that we have the adiabatic process. And, so this is according to the adiabatic theorem, right? We'll achieve this ground state at the end. But it's difficult to ensure that we have really adiabatic process. So this is one thing. Another thing is that the strength of the magnetic field should be changed slow enough. And there are even formulas um, showing how slow this change should be in order to ensure that we will stay in this ground state. Uh, so sometimes for some problems, this should be so slow that we cannot just expect any practical advantage. But there is a hope, and the hope is that, instead of, let's say, looking for the best possible solution to our problem, very often it is sufficient for us to find solutions that are, let's say, good enough. We cannot prove that our solution is really optimal, but um, very often in practice, the solutions that are, for example, 1, 2% worse than the best possible solution are still acceptable. So maybe we can just accept the fact that it's difficult for us to ensure that we'll stay in the ground state. So we'll find the global minimum to our problem. But maybe we can just do this annealing a bit faster. So we cannot guarantee that we'll stay in the global optimum. But there's still hope that we'll find a relatively good solution. So that's the idea behind this annealing. And here earlier I mentioned the icing model, but let me check the chat first because I saw that there were some questions. Um, so there is a question from Bartek, or actually there are two questions. The first is, do you see any potential applications of real random number generator, even as a feature in an electronic processor like cryptography, identity verification? Yes, indeed. I heard about such ideas. For example, to organize um, the electronic elections, the electronic voting, um, with support of quantum random number generators and quantum key distribution, quantum communication. So there was also something that was called quantum Byzantine agreement problem. So there are such ideas, right? But as far as I know, it's difficult to achieve, and I'm even not sure if it's really scientifically valid at the moment. Some people specializing in cryptography rather says that we shouldn't expect safe electronic voting in the nearest future, at least. Um, but regarding cryptography, identity verification, yes, I think you might be right, especially cryptography. Because very often in cryptography we have to randomly sample some numbers, and there could be some attacks uh, on the on the bad implementation of our random number generator, right? So I believe that indeed there could be some applications in cryptography. I'm not sure about this identity verification. Perhaps there can be, but I'm not sure how important it is to have this real random number generation. And there is another question: is there a chance to bypass the boundary of efficiency of electronic processors associated with NP problems by using the quantum processors? As far as I know, it's still an open problem, um, but probably not. So, so the hypothesis is that at least the quantum computers that I've introduced to you, most likely they will not be able to solve NP problems in polynomial time. I think it hasn't been proven formally yet, but uh, I'm al almost certain, because if we prove it, then I believe that could probably also prove that we can also do it in classical computers already. But there are some other ideas, For example, there is a very good, famous researcher from Jagiellonian University in Krakow, Dr. Jarek Duda, who proposed an idea for something that he called a two-way quantum computer, in which the state preparation is not only on one side, but also on the other side of the quantum circuit, some qubits. There could be the state preparation in case of some qubits, so that we can enforce a behavior of some qubits and then do the measurement on the remaining qubits. And in this case, we can already theoretically prove that we should be able to solve NP problems in polynomial time. But the problem is that we do not know if such a computer can be built at all. It's also an open problem. So Jarek Duda says that if we cannot build it, then we have a macroscopic violation of the CPT symmetry. And as far as I know, physicists believe that it will not happen. Uh, but I feel that I do not have enough knowledge and understanding of the CPT symmetry to validate it. So from my perspective, it is an open problem. I hope that it answers your question, Bartek. Um, okay, let's go further. So here I mentioned the LXIX model, right? That we need uh, to prepare a Hamiltonian corresponding to the LXIX model. So what's the LXIX model? So the LXIX model is a model of ferromagnetism traditionally used in statistical mechanics. So here the variables are spin up or spin down. The states correspond to +1 and -1 values. So this could be atomic spins or magnetic dipole moments. And there are some relationships between the spins represented by couplings. There are correlations or anti-correlations. And there is the objective function, Hamiltonian, expressed as an Ising model as follows, right? So here we have some coefficients. These are the qubit biases. These are the coupling strengths between these different variables like atoms. Uh, so And this is the formula for the energy. This is the Hamiltonian in this case, right? And depending on the value of Si, Sj, we can calculate the value. Okay, and in computer science, we have something similar that is called QUBO, quadratic unconstrained binary optimization problems. So here we also have binary variables, but their values are 1 and 0, so this is the difference. And we can also formulate these quadratic unconstrained binary optimization problems in this way, right? So we have binary variables xi, we have some coefficients, okay? And this is the function that we want to minimize. So we want, in this QUBO problems, we want to find the assignment of values 0 and 1 to the variables xi to minimize the objective function. And you can see that these functions are very similar, right? So actually the difference is in the possible values +1, -1, which means that if we are able to define our optimization problem in using this formula, uh, we can we can we can encode it. I need to mute someone. We can encode it in a ferromagnetic, and we'll have the Ising model for this. So the energy of the quantum states in our quantum system will correspond to the to different solutions of our optimization problem. And then by changing the strength of the magnetic field, we can perform the quantum annealing. Um, so this is the idea, right? So now the whole idea is to define our optimization problem in this way, in such a form as QUBO, and then we already know how to encode it in the quantum annealer, and then we know how to, let's say, force the nature to perform computations for us. So we do not tell exactly how to perform computations, but we just take advantage of the laws of physics and quantum mechanics, like quantum tunneling, for example, right? So this is one of the quantum phenomena that exists in quantum mechanics and not in our classical world. So by controlling and changing the strength of the magnetic field, and just a reminder, we have to do it slow enough, we change the landscape of our objective function, right? So we start from the relatively simple function for which the minimum, the ground state, is easy to prepare. And then when we change the strength of the magnetic field, we change the landscape, right? So just coming back here, right? So we start from a simple function. Here is a more complicated Hamiltonian, and by changing the values of s, we change the landscape here, right? And as our system at the beginning was in the one ground state, when we change the landscape, then it may turn out that this point is no longer the global optimum, but it may happen that thanks to quantum tunneling, we can, or the system may jump to another possible solution that is relatively good. So this is how it works in theory. How exactly it works in practice is, I think, more complicated, and currently the quantum annealers are developed by, I think, only one company in the world that is called D-Wave. It's in Canada. And in the past, there were some controversies about the technology as well, but they recently started publishing some interesting research papers. So this was also one of the reasons of the controversies, that some parts of the research was not published, not transparent. So it was difficult for the scientific community to validate it or accept some results that they claimed to achieve. But I think that recently the situation has changed, and I will tell you about it later. But I also wanted to give you an example on how exactly this quantum annealing can work. And the example is from the transportation domain. I can say it's my favorite domain because I've been working in the transportation field for more than 15 years. And actually, this is a very interesting story. I will not tell it today, of course, but I can tell you that I started working in the quantum computing field thanks to working in the transportation field earlier. because I was very interested in solving different optimization problems in the transportation domain, and at some point I learned that there are already some ideas on how to employ quantum algorithms to solve some optimization problems in transportation, including the problems that were interesting for me. And here is an example. This is an example of the something that's called route assignment problem. Researchers from Volkswagen used quantum computer from D-Wave, or this quantum annealer, quantum annealing machine from D-Wave, to run a traffic flow algorithm on a quantum computer with, and they achieved encouraging results. And as you can see, this is a publication from 2017, so it's already more than 8 years ago. And here is a link to the paper that they published. The title is Traffic Flow Optimization Using Quantum Annealer. I recommend you to read it. I think it's very interesting and it's not very difficult to understand. And I will try to explain their idea because I found it inspiring in some sense. And I think it's a good example demonstrating how exactly we solve optimization problems using quantum annealing. So this is what they did. So first they built a road network, a realistic road network, and it was from the data, probably from the OpenStreetMap. It's an open data set of road networks on the world, and they had routes from real GPS navigation systems from taxis in Beijing. There was a data set called T-Drive. It was open and developed by, I think it was developed by researchers from Microsoft Research. So for every taxi, they had the exact route. I think it was the route from the city center to the airport in Beijing, in China. And they added two possible routes between the source and the destination. And so for every car, there were three available options. And it was assumed that cars may share road segments. And it was also assumed that the travel time is proportional to the square of a number of cars on a route, which is a simplification, but it is a realistic simplification because when you think about it, there are some regimes of traffic density where the travel time is mm, linearly dependent on the density of cars. So when we calculate the aggregated travel time of all cars for a given traffic density, it's a square function, more or less. So it's an approximation and it's a simplification, but it's not that far from the true. And now the goal is to minimize the total travel time, right? So what they did, they introduced the binary variables qij equal to 0 or 1. So it was assumed that the value of the variable is 1 if the car I takes the route j, and otherwise the value is 0. And this is a condition that has to be satisfied for all cars. When we look at all these three variables for a given car, because for every taxi we had three routes, one route from the real world data from this T-Drive data set, and there were three additional routes, additional options added by the researchers, right? But only one of these three variables should be equal to one, and exactly one variable should be equal to one because we want every vehicle, every car to take exactly one route, right? So this condition has to be satisfied. And here we have a set of the variables, these binary variables associated with routes that share the street segment S. So what's the total cost of travel time? The total cost of travel on this route, right? So here we have the sum of all these binary variables corresponding to the vehicles taking the route that involves the street segment S. So this this sum is equal to the number of cars that select a route going through the road segment S, right? So this is the number of cars on the route segment S. And here we have the square because we assumed that the travel time is the square of the number of cars traveling through a given road segment. And I already explained that this is a simplification, but it's quite realistic. So now the whole objective function is the sum of all these costs for all road segments. And we can easily see that the minimum of this function is just 0. When we just set all the values of the variables to 0, then the minimum is 0. But it's not interesting for us because it would mean that we do not have any traffic, right? Because this condition is not satisfied, right? When all the values of the variables q are 0, then this condition is not satisfied. So we have to ensure that this condition is satisfied for every car I. And in order to do it, we calculate another formula, right? That is equal to 0 if and only if all the conditions are satisfied. And here we have a very large coefficient, lambda. And now the idea is as follows. If the condition is not satisfied, then this value on the right part is very, very large because it's multiplied by a large coefficient. So our quantum solver or any classical solver shouldn't consider such solutions as valid solutions, as feasible solutions. So our solvers will look only for solutions for which this component is equal to 0. And then under these conditions, they will try to minimize the first component, the cost function. Because otherwise, the value of the objective function will be very large. So our solvers will not consider these solutions as good. And luckily, both the cost function and these additional constraints are also in the form of a QBO, which means that we can encode this problem in the D-Wave quantum annealer and perform computations. And this is what the researchers did, indeed. So they had 418 taxes, so there are 3 times more logical variables. The space of possible solutions was astronomical, 3 to the power of 418. So, of course, it's not possible to check all possible solutions, right? It's not feasible on classical computers. And the result of applying quantum annealer was a relatively small number of streets that were heavily occupied. So here on the left, you can see the visualization of the solutions for, visualization of the real traffic in Beijing. The more red color means that there are large delays and large density of cars. And on the right, you can see the distribution of routes, these route assignments found based on the solutions found by the quantum annealer. And the time of computations was only 22 seconds, which is quite good. But unfortunately, in the original paper, there was no information about any comparison with classical algorithms. So this problem is difficult because, the size of the space is very large. But at the same time, uh, it's quite likely that there also exist some very good classical algorithms able to solve this problem in relatively fast, or at least find relatively good solution. Maybe not necessarily the optimal solution, but let's say good enough. So there could be some heuristics, meta heuristics like genetic algorithms or other evolutionary algorithms that could be applied to solve this kind of problems classically as well. So it doesn't mean that we have the quantum advantage, but it means that the quantum annealers can be already used to solve some real problems, real practical problems, and provide some relatively good solutions. So that was a very nice paper. Actually, the idea was very inspiring for me as well. And later I also started working on solving some other problems in logistics, like the traveling salesman problem, the vehicle routing problem, and its variants using quantum annealing and other quantum algorithms. Also, in the circuit-based models, like using variation quantum algorithms. And there are already logistic companies interested in such solutions because the whole logistic domain is very large, so it's a very large market worldwide. And as these kind of problems are NP hard, then any improvements can lead to significant savings in a large scale. Okay, it's also good to tell a few words about quantum machine learning because I said that the machine learning in general is all about optimization, right? So when we talk about optimization, it's good to talk about how quantum computers can be used in combination with machine learning, with classical machine learning. So actually, it's good to know that we can think about different combinations of classical and quantum computing in terms of machine learning. So we can think about using quantum algorithms to solve some classical problems, like the same problems that we can try to solve using uh, using uh, mm, classical machine learning algorithms. Uh, but we can also try to apply classical machine learning algorithms to solve some computational problems from the quantum sciences related to quantum technologies. Um, and in my opinion, it's currently it's even more promising to try to use classical machine learning techniques to solve some problems from the quantum domain. Of course, we can apply classical algorithms to solve classical problems, but this is just standard classical machine learning. I said just, but nowadays we know that AI is literally eating science, and there are Nobel Prizes for applications of AI. So even this left upper corner is very, very powerful already, even without quantum computers. But when we talk about application of quantum computers, I rather believe that this field at the right bottom might be more promising. So applying quantum algorithms to solve some quantum problems on quantum data. All right, but let's tell a few words about, or a few sentences maybe, about the application of quantum algorithms to solve classical problems. So in this case, contemporary computers, as you know, are still noisy. So we live in the so-called NISQ area, noisy intermediate scale quantum area, in which we have these NISQ devices that are small and noisy. There are the quantum circuits we can build and run are relatively shallow. It turns out that there is a class of algorithms that seems to be quite suitable for this kind of devices that we currently have, and they are called variation quantum algorithms, or VQA in short. They share a common structure where a task is encoded into a parameterized cost function, the so-called ansatz, that is evaluated using quantum computer, and there is a classical optimizer that trains the parameters in the variation quantum algorithm circuit. So here the optimizer is classical. We can also think about maybe some quantum optimizers, but currently for the contemporary quantum computers, we still rather use classical optimizers. But perhaps we can also think about using quantum annealing here in the future, if possible. I believe that based on the structure of the computing loop in this case, it can be difficult. But who knows? We'll see. Um, so in this case, we use this parameterized quantum circuits, so parameterized gates, parameterized rotation gates that I also explained earlier at the beginning of this lecture. Yeah, and when we talk about this quantum machine learning, um, it's good to know that there are already research papers about or trying to apply quantum computing to all kind of classical machine learning algorithms. Like there are quantum generative adversarial network, quantum reinforcement learning, quantum SVMs, and so on. It doesn't mean that they can all give advantages, but there are already some research papers claiming that they achieved some, that the researchers achieved some advantages by adding some quantum components to some, let's say, classical models. But in general, in machine learning, it's very difficult to prove anything. And in this case, we also cannot prove that there is any real advantage that there cannot be better classical models. I believe that in most of the cases that have been published and demonstrated nowadays, there are also some classical models that can be even better. But anyway, if you are interested, at the end I will also give some sources to more information about this quantum machine learning, or actually rather quantum enhanced machine learning in this case. Because another area of the quantum machine learning is when we apply classical algorithms to solve quantum problems on quantum data. And here we have some examples like quantum state tomography, which is a process by which a quantum state is reconstructed using measurements on an ensemble of identical quantum states. There could be a quantum feedback control, quantum circuits optimization. And if you are interested in more application, there's a very nice review article co-authored by Anna David and several other researchers about modern applications of machine learning in quantum sciences. Okay, that was the next section, and we have the last two sections of this talk. Let me check if there are some questions on the chat. I do not see more questions, so let's continue. What's the progress? It's good to acknowledge that there is progress in the development of contemporary quantum computers. I will later show you that there are different techniques, different technologies to build quantum computers. But I am in this field from more or less 2017, and I can tell you that I have observed visible and stable progress. The progress is not as fast as in the case of artificial intelligence nowadays. It's a totally different magnitude. It's a totally different level. It's much smaller, of course, in smaller level on the space in the case of quantum technologies and quantum computing, but it is visible. It is visible, and that every year there are some important breakthroughs. There are some important research papers and announcements from companies building quantum computers. Like just earlier this year, Microsoft unveils Majorana 1, which is the world's first quantum processor powered by topological qubits, but actually later Microsoft admitted that they can say that they have just a half of a qubit only, right? So there are different approaches, there are different technologies to build quantum computers where we can already have more qubits, like even a few thousands of qubits, like in case of these D-wave machines. And earlier this year, I think it was February or March, this D-wave company from Canada working on quantum annealing published a paper in Science with the nice title Beyond Classical Computation Quantum Simulation, and they actually demonstrated a use case related to magnetism, which was not, let's say, it was natural to expect that this could be a good domain for them, for the quantum annealers. And they, let's say, scientifically demonstrated the advantage of the quantum annealer over some classical computations. And they claimed that this is the first practical demonstration of the quantum advantage on a practical problem. Uh, because earlier, like in 2019, there was the first paper from Google demonstrating the quantum supremacy. But first of all, there were some controversies around it. There was discussion with researchers from IBM who said that these computations can be still performed on the best, the fastest classical computers, but they didn't demonstrate it in practice. And also the problem was rather artificial, so it was constructed just to demonstrate that we already have this quantum advantage, but there were no practical applications. But in this paper from this year, these researchers from D-Wave claim that they achieved the first practical quantum advantage on the, let's say, it was not a business problem, but rather an open scientific problem that they solved using their quantum annealer. Okay, but anyway, I think we can still say that we still live in the NISQ area, even these quantum annealers are also noisy. So here a few words about this quantum supremacy that was announced by Google in 2019 using a programmable superconducting processor. So I've told you that there were some controversies, but I think that after several years, or during the last several years, there were some other demonstrations of this quantum supremacy for some other cases. So I think that currently we can say that we already demonstrated the quantum supremacy, but we can do it mainly for some rather artificial problems. Here was another paper, this time from IBM, as far as I remember, cutting through the noise. So there was also demonstration that even in this uh, contemporary noisy quantum computers, we can still achieve relatively good results. Uh, the researchers suggest that with error mitigation, existing and near future quantum computers might be good enough to help with problems that are beyond the reach of classical machines. And this was published in Nature. So there are scientific papers demonstrating that there could be an advantage in the future, and maybe relatively soon. It's good to know that there are different approaches to build quantum computers, like based on ion traps, superconducting qubits, there could be photonic qubits, neural atoms, topological quantum computers. So here I still say that it doesn't exist yet, as you know, because Microsoft later admitted that they have half a qubit, not even a single qubit. Then I think we can safely say that even though they achieved a breakthrough that they announced this year in the International Year of Quantum Science and Technology, we cannot really say that we have any reasonable quantum computer yet. Okay, what can be the future? There was a nice quotation attributed to many people. I think that let's say, the oldest living person on this list is probably Abraham Lincoln, that the best way to predict the future is to create it. So it's good to know that there are still some obstacles on the road toward quantum supremacy. So there is a limited quantum state duration, and then we have the coherence of our quantum states when we lose the coherence and lose information that is stored in the quantum system. There is a noise, but so there is a need for error correction and error mitigation. There is need for algorithms, for new quantum algorithms. So actually, there are still not that many quantum algorithms for which we can prove that they can be better than their classical counterparts. And when we can prove it, so even for the Shor's algorithm, there is no formal proof because we haven't proven that we cannot factorize numbers in polynomial time using classical computers as well. And from the engineering point of view, building some quantum gates is still challenging. I see there's another question. For neutral items, what company can achieve 1,500 qubits? I think it was 1,180. Let me check it. It was Atom Computing, 2023, 1,180. Maybe it's possible that I'm not aware of some new announcements. So there are so many news from both the AI and quantum field. I try to follow the most important news, but it's always possible that I missed some announcements. So it's possible that these numbers are outdated a bit. But this is just to give you the information about the order of magnitude. Uh, all right. Yes, going back to the future, to the next slides. So regarding the quantum error correction, so there is some information about it. Um, we already know that the quantum error correction codes exist at all. So there was a stunning proof in 1995, and there was also a proof that these quantum error correcting codes could theoretically push error rates close to zero. And this was the central discovery in the 90s that convinced people that scalable quantum computing should be possible at all. This is what Scott Aronson said. He's a famous researcher from the University of Texas. And he said that it is merely a staggering problem of engineering. So it's more an engineering problem and not scientific problem. And actually, just last year in 2024, maybe you heard about the announcement from Google. I think I also included this here on the list of this, let's say, important milestones. So Google announced the improved error correction, and actually, as far as I understand and heard, they just demonstrated how to build a scalable error correction in practice, at least for some problems. Maybe not all problems, but at least for some class, for a class of problems. So what Aronson said some time ago, that it's a staggering problem of engineering. So it seems that thanks to Google, we know more or less how to solve this engineering problem, at least for some cases. So here I'm not an expert in quantum error correction, so I'm afraid I cannot tell much more. But if you are interested, I will later tell you that in November we'll organize a workshop on quantum error correction. It will be led by our great instructor Alex Linden, and she can tell you more about the quantum error correction. but just to let's say give you an idea on how this quantum error correction may work. Let's imagine a simple quantum error correcting code when uh, we just for a single uh, qubit or value zero, logical value zero cat, we construct three physical qubits with initial state 000, and the same for um, the value 1. And if we assume that there's at most one qubit that suffers a bit flip, then when we get the results of our computations, we can know what's the correct result, right? So, for example, when we achieve 010, and we know that there's only one error, right? Or up to one error on one of these three qubits, then we know that the correct value was 000, for example, right? So this is just a simple example, but there's also a strong assumption that at most one qubit suffers a bit flip. I also said that it's difficult to prove the quantum algorithm will be better than classical. And here I have another interesting uh, mm, news that I wanted to share with you. The same Scott Aronson proposed to his genius student, PhD student Ewing Tang, to demonstrate that something that was called a recommendation problem is an example of quantum advantage. That because there was a polynomial time quantum algorithm that was known, but and it was believed that this problem is difficult for classical computers. And as far as I heard, she first tried and she was given the task to prove that there is this quantum advantage in this case. But contrary, based on or being inspired by the quantum algorithm, she demonstrated how to build polynomial time classical algorithm for the same problem. So this is an example of how quantum computing can inspire classical computing and move the classical computer science forward as well. This was very nice, but it also demonstrates that it's very really difficult to prove the quantum advantage, even in theory. Even for the Shor's algorithm, we do not have it. We have it for the Grover's algorithm. Okay, I also told you that we have these NISQ devices, right? So there are some programming frameworks for these noisy intermediate scale quantum devices, like Circuits developed at Google. I think that is also something that I discussed. It's good to know that there are also some other programming frameworks like Qiskit, probably still the most popular. So here we can see the code in Python, and it just creates a belt state. When we have two quantum registers, two classical registers, we apply the Hadamard matrix to one qubit, and then we entangle two qubits. We apply the CNOT gate, and then we measure the results and then store the results on the classical registers. This is PyQL from Rigetti, another Python library. Project Q developed at the ETH Zurich. It's an open source project, another Python framework. D-Wave it's a framework for quantum annealing. So if you want, you can create an account there. And I'm not sure if it's still possible to get some free computing power for the quantum annealing. Maybe not, but if you are a researcher uh, affiliated at academic institutions in Poland, you can apply to have some to have access to this D-Wave framework for free for scientific purposes only, of course. YAO.jl is an example of a nice library for quantum computing developed in Julia, not in Python. Um, yeah, so Julia is a nice programming language, and some people says that it's even much better for quantum computing than Python. For example, thanks to the ability to parallelize computations, like if you want to simulate some quantum computations in a classical way, then I heard that Julia is very good for this. Penelane. So it was the first library for quantum machine learning. So that's why it was, for some time, it was called the TensorFlow of quantum computing. It was developed by another company from Canada, Xanadu. So here we can see that we have two parameters. We create the parameters quantum gates, rotation around the axis x, y, and we have parameters we calculate the cost function and calculate the quantum gradient. So yeah, this is just an example of a simple code. But uh, later Google released TensorFlow Quantum. So that was a quantum library for the TensorFlow framework. There was also, maybe there's still, the quantum machine learning model in Qiskit framework as well. Okay, let's see if there are some questions on the chat. There's a question: which companies are commercialize their machines? Many companies. D-Wave is one of the examples. They already sold many quantum annealers. There are also some other companies that have solved some quantum computers. So I can tell you that here in Poland we have two quantum computers from Orca. It's a British company, and they are photonic computers. There is one quantum so they are in Poznań, in the Poznań Supercomputing Center. There's one quantum computer, Odra 5, is based on ion traps from it's a quantum computer from IQM. It's a company from Finland. It's based on ion. The technology is based on ion traps, and there are 5 qubits. Yeah, so these companies already sell the quantum hardware. Uh, what's the applicability of this quantum hardware is another thing. So some people just want to advertise and to cheer the fact that they already have quantum computers, even if they are not very practical and they are not very useful. It's it's good to tell that okay, we already have a quantum computer, and then there's always a question what we can do with this quantum computer. So usually these contemporary quantum computers are very good for educational purposes, of course, but perhaps having access to computational power in the cloud can be sufficient. They can be also used for scientific purposes, but the application in science is limited because they are still relatively small and they have very limited industrial applications. Maybe this D-Wave quantum annealer. So D-Wave frequently says that they already collaborate with some companies and they achieve something that they call a business advantage, not the quantum advantage, but business advantage, that they are able to solve some business problems using their quantum annealer that were not solved by classical methods earlier. They cannot formally scientifically prove that it's not possible to solve these problems using classical algorithms, but they demonstrate how to do it using quantum computers, and sometimes it can be easier and faster indeed to implement something because you saw that you have seen that um, solving something using quantum annealing is not that difficult. So the most difficult part is to find out how to encode your optimization problem as the quadratic unconstrained binary optimization with relatively small number of qubits, with a relatively small number of variables, because you need to encode your model in a quantum annealer later, right? But there are already many companies that have commercialized their machines. Okay, and now about the quantum ecosystem. So I will start from the organizations and activities that I'm personally involved in, because I'm currently the chairperson of the board of QWORD. QWORD is formally it's a non-profit organization registered in Estonia. It's a non-profit organization. It's a, let's say, international organization, we can say it. It's a global network of individual groups and communities collaborating on education and implementation of quantum technologies and research activities. So I can say that our goal is to democratize access to quantum technologies, right? To ensure that people all over the world have, let's say, relatively equal access to quantum technologies. We organize multiple events. We develop educational materials together. We have several departments like Q Education department, Q Research department. We organize workshops on quantum computing and programming. Just 2 days ago, the next introductory level workshop, Q Bronze, organized by um, the Quantum AI Foundation and Poland, so I will later tell about Poland as well, was finished. So at least we finished the sessions because now the participants still have more than 1 week to complete their homeworks, their quizzes, in order to get a certificate. As Poland, we've handed out more than 700 certificates, and the whole Q world has handed out more than 10,000 certificates for sure, maybe more than 20,000 already. We work together internationally to develop these open and free educational materials. These materials are available under the Apache 2 open source license. We aim to build the complete quantum curriculum for the complete quantum studies and quantum technologies. Um, so I think that we are at the level of having something like a quantum semester. Um, Maybe we have something like Q course. We have something like Q class. So they are something like long-term courses on quantum computing. Um, Q Intern is another interesting project of QWORD. It's a matchmaking event for online research internships in quantum computing. The idea is as follows. First, some senior researchers propose the ideas for research projects, and then students from all over the world can apply, and we match them, right? We match researchers with the students, and if they decide to collaborate, they work together during the summer, and then at the end of the summer, there's something like the demo day when they present the results of their work. Few cousins. So I've told you that Keyword is a global organization, but we have local communities all over the world, the so-called Q cousins. There are more than 30 Q cousins worldwide. So some of them are currently inactive, but we hope to re-entangle them again. So we call this process of establishing new Q cousin groups in new countries the entanglement workshop. We organize something like the entanglement workshop. Um, yes, so eventually we would like to engage every country, of course. So in particular, we have Poland. In Poland, I'm also lucky to be the coordinator of this group. We organize multiple events here in Poland. As you can see, we have representatives, researchers from different universities or research institutes in Poland. And I think I can say that QPoland is one of the most active Q cousins in QWORD. It's also one of the 5 founding members of QWORD because initially there were 5 Q cousins: Q Latvia, Q Turkey, Q Hungary, Q Poland, not Q Russia. Q Russia joined later. There was Q Balkan that was later rebranded to Q Bosnia. So initially all these Q cousins were in the Central and Eastern Europe, and then later this network has grown. So now we have Q cousins in 5 continents. We do not have Q Australia yet, but we hope to have Q Australia soon as well. So here are just examples of some initiatives that we organize as Q Poland, and as I've told you, the Quantum AI Foundation is a formal legal supporter of the Q Poland's activities here in Poland. We organize workshops on programming quantum computers. As I said, we've handed out more than 700 certificates. We organize joint meetups with quantum computing groups from Warsaw, Toronto, and Washington, D.C. We organize hackathons. So next week on October 18, we'll start our fifth hackathon, quantum hackathon. The name is Poland Global Quantum Hackathon. You can still sign up by October 17th if you want. We organize a contest on popularizing quantum computing. So this contest is only for people from Poland, for high school students and for university students. We organize a conference on quantum machine learning. We've already organized 5 editions. There will be sixth edition in 2026. You can find information how to join us on our website. And yeah, on this weekend, actually, we also have the quantum machine learning workshop. You can still register until tomorrow. And in November, we'll have another workshop, this time on quantum error correction. It's called QThink. And we also release a monthly newsletter, QPoland newsletter. So you can subscribe to stay up to date with the curated news from the quantum world. So yes, I want to invite you once again to attend this quantum machine learning, this Poland Global Hackathon and this quantum machine learning workshop, of course. So a few words about the other important elements of this quantum computing ecosystem in Poland. It's very important to know and to acknowledge that Polish science has played an important role in the development of quantum computing. There are at least a dozen research groups carrying out research in the field of quantum technologies at different universities and different research institutes. There are at least several Polish startups and companies that carry out research or create products in the field of quantum technologies. So actually, we are now working on mapping the whole quantum ecosystem in Poland, and we know that there are already more than 50 entities dealing with quantum technologies. I believe that we'll have closer to 100 um, soon in the final map. There are also two non-profit organizations supporting the research education. Fundacja Quantum AI is proud to be one of them. There are several meetup seminars organized that are others to enthusiasts in quantum technologies. There are several social media groups and profiles dealing with quantum technologies as well. There is a large human potential and good quality of education in the field of computer science, math, and physics. I hope it will not change and there will be no significant changes in the educational content in our schools. And besides QPoland, there are also some other efforts to integrate quantum community in Poland. Like there is a cluster Q, there is a Quantum Technologies Committee of the National Chamber of Commerce. You can read more in a report that we published a few years ago. The title was Czas, Time for the Digital Economy. In Polish, it's Czas na cyfrową gospodarkę. It was, as far as I remember, it was in Polish, so probably only people from Poland can or everyone can check it, of course, if you are interested in the Polish ecosystem, quantum ecosystem, but can be more difficult for you if you do not know Polish. And we are now working on the Polish quantum strategy. It will be formally called the Policy for the Development of Quantum Technologies in Poland. We've already published the assumptions for the final document, and there were public consultations until the end of September. And now we are working on version 2.0 of these assumptions. Yeah, we received more than 20, about 20 uh, uh, documents from people. Um, yeah, if you develop some open source projects, you can apply for um, some grants from Unitary Fund, for example. There are micro grants, $4,000 in cash, but you can try to get it if you do something interesting and open source in quantum technologies, of course. Where to learn more? So here are some useful links to the website of QWorld. Of course, there is a nice course on quantum machine learning at LXIX. There are some videos on YouTube from Peter Witek from University of Toronto. Um, and there are some Facebook groups that we created and we moderate. You can check the social media profiles. I also shared the links area at the beginning, and here you can see more links. Just recently, we also created even an Instagram profile of our Quantum AI Foundation, and there's also a TikTok profile as well, because we are just planning to organize some new educational activities supported by some companies for which the activity or our activity on Instagram and TikTok are important. Um, yeah. So I thank you for your attention. I hope you enjoyed. I will be happy to answer questions from the chat soon. But before that, I would like to thank once again our strategic partners for supporting us. Sonovero R&D, AIQ Lab, Quantum Z.io, Onyx, Cogit, and I think Qubit. And thank our honorary partners as well. Finally, if you like our activities, you can also donate. If you pay taxes in Poland, you can also donate 1.5% of your tax for support our activities. And all the activities that we organize are free for participants, so we rely only on donations from our supporters and sponsors. We also invite you to the next episode. It will be on October 13th, so 3 weeks from now. Radu Marginean from Romania will give a talk about two new tools for quantum computing. So I know that they developed something useful and interesting there in Romania. So I would like to thank you for your attention, and let me check the questions on the chat. Yes. Um, okay, there is a question from Park Shen Honk about can you give some advices or share your experience on how you keep Poland active, engaged with the community? Um, it's hard to say. I just try to be active personally as a leader. There's in Poland we have a nice quotation that says that an example always comes from the top. So when you are active as a leader and you inspire your community, then people will follow. So uh, this is my main advice. I think that if you organize something, then you have to be also very active as a leader, and you need to inspire members of your community. Mm, yeah. Uh, so I think this is one thing, and it's always good. Also, also always good to find some sponsors of your activities, even if you organize events that are free for participants. When you have some sponsors, you can always try to pay people for some activities, like being an instructor. We usually try um, to give some remuneration to our instructors of the events. Um, so uh, it depends. But we also keep a Discord server for our community where we publish many news from the quantum world. Uh, so it's there's always a point where that you need to reach first uh, in order to ensure that the other people will just follow you. There is another question from Tomasz. How Poland stands as research place in quantum algorithms area? Is there a possibility to do master's PhD in this area in Poland? Yes, I agree with the answer that comparing to the China, US, UK, it's not that good, but in general, comparing to other fields in Poland, in other fields of research, I would say that physics, computer science, math areas are still relatively good. So we have at least a few good quality universities and at least maybe less than 10, but let's say something between 5 and 10 relatively good research groups publishing papers at good conferences in good journals. So it's not that bad, but it's a totally different scale than the scale of the US, China, and the UK. But if you want to do your master studies or PhD in this area, you will find some places and you will find some good supervisors for in most of the areas that I discussed today. Right? So there are some options. You do not need to go abroad to study or do PhD in quantum technologies. Definitely. Yes. This is true that we are one of the last countries working on the quantum computing strategy. There are some awesome quantum physicists indeed. So regarding this quantum strategy, an interesting thing is that just recently I learned that Switzerland is also working on their quantum strategy. They also do not have the quantum strategy yet. They have something like a quantum program. There's something like Swiss Quantum Initiative, but they do not have something like a long-term quantum strategy yet, which was interesting. So, I agree that we are one of the last countries, but but there are also some other countries who are working on their quantum strategies right now, as Poland is working on its quantum strategy. So, okay, do we have more questions? Um, I think I do not see more questions on the chat. Maybe someone would like to unmute and ask a question. You can always reach me out later. I provided links to my website and in my email addresses, so you can reach me out later as well. All
Paweł,
right. Yes,
can I just say something?
yes, yes,
Thank you
please.
very much for this, Slavek. Thank you very much for a great presentation. The one thing you mentioned, you're working on the ecosystem of the startups working on quantum. Actually, my
Yeah,
team done already this, so I will drop you an email and we'll share that if you're interested.
but could you please repeat what exactly you will share?
I will send you the list of all the startups that we already mapped, that we have already in Poland, actually across Europe, to be fair, super country. the
Okay,
valuation, what they do specifically, what kind of projects they're working, and
okay.
the whole
But
thing.
it is for startups only, right?
It is for all the companies that they produce something useful.
Oh, okay. Feel free to share it. Thank you.
You're welcome. Thank you.
Thanks. All right. So in this map that we are now developing here in Poland, there will be, of course, companies, startups, but also research groups, universities, NGOs involved. So yeah, perhaps there will be maybe more, but we'll see. Anyway, it seems that in Poland there are more than 50 organizations, groups working on quantum technologies. I think it's closer to 100, but we just haven't mapped all of them. We created a survey, right? So we ask different companies to just fill in a survey to tell us the details about their activities. All right. Thank you. Thanks, Bartek. I appreciate it. I'm glad that you enjoyed. So I will now stop sharing my slides and I will also stop recording. And I hope to see you on our next events. So just to remind you, the next Warsaw Quantum Computing Group meetup will be on October 30th, but the quantum machine learning workshop that we organize will be this weekend, and you can still sign up and participate for free. Thank you once again. Have a good evening, everyone, and hope to see you next time. Bye bye.